So if f is a function and it's defined in this interval that I'm interested in between a and b, we can divide the interval. As we've seen, this is all kind of review stuff, just kind of clumped together here. We can divide it into how many subintervals I want, ideally with equal width, which would be called change of x. So we're going to add up all of these things, height, width, that means add up height, width, starting with 1, going to however many we have. So if I'm going to estimate by adding up, this is what the definite integral looks like right there. I'm going from a to b of some function, and I'll explain all this in a minute. D of x, that tells me the variable at which I'm focusing on here, is approximated by doing this. Starting with 1, going to however many subintervals I have. Height times width, height times width. Okay. And we say that f is, we've seen this before, integrable, at least between a and b. We don't know what's happening after or before a or after b. The integral is a limit of sums, so this is called my integrin right here. This is the limits of integration. That's the lower bound, that's the upper bound, or that's the left side, that's the right side, because I'm going for values of x. Okay, and I've mentioned before, this is, so I've sort of copied stuff from other stuff because I'm trying to summarize here. So this thing right here, it is all one symbol. So you're going to get one numeric value. Just like if you would do the cube root of something. So when we see dx in that formula here, that just says, hey, that's my independent variable. That's the variable I'm going to focus on here. Sometimes you might see dt, which means I'm going to focus on t. We could reference any variable. This process of calculating an integral is called integration. Okay. So we're estimating using Riemann sums, a lot of rectangles, either the right side, left side, or midpoint. Okay, we've done all that. Hopefully we've gotten practice with that, right? So a Riemann sum is the sum of the areas of rectangles that lie above the x-axis but less than the areas of the rectangles that lie below the x-axis. So it's the upper above the x-axis minus what's below. So it will approximate the net area under the curve. So when I take a definite integral, here is what it's giving me. Area above minus the area below. It's giving me the net area. We may be able to take an exact value of this net area. When I do, it's still going to be net area. And when I do Riemann sums, it's still going to be net area because I'm going to subtract anything that has a negative area. That's going to be part of adding stuff together. You'll see that, oh, this one's underneath, so it's negative. It's going down. If you plug it into the formula, you're going to get a negative y. So you're going to do width times a negative y. It's going to take away from your total answer. That's why I say it's net. Be careful. If a problem is asking you to find the integral, it's asking you to find the net area. Or they might even say find the net area, which is finding the integral. So when you find the integral, or either actually exactly or through any kind of estimate that we've learned or approximation, you're finding the net area. So if you find the net area, this and this, that's it. They might say find the total area. If they say find the total area, I'm always cautious. They're saying find the total area. Does that mean it's going to be different than the net area? I better check. Because if I'm getting any negatives here, that's pretty easy to see. because you're having to plug it in each time, you're gonna see a negative height. I would have to add that back. Turn that to positive absolute value to get a total, okay? We'll play with it when we get to the exact way, how I have to do it. But just remember, if you want total area, you're gonna have to add back anything that was negative. Because you took it away to get that. Total area, you're gonna have to add it back. And if you're estimating, you're gonna see, hey, any of those negative heights that you got, make them positive and add them back. Absolute value though. Okay. Not all functions you can take the integral of. But most of what we're looking at, you can. So as long as f is continuous, at least where I'm looking between a and b, we're good. We are good. Remember, so many of our functions were continuous. So many. So we're good. But also, this is interesting, guys. If f has a definite number of jump discontinuities, here's what that means. So between a and b, let's say here's a, there's b. So as long as I'm continuous between a and b, hey, I can get the area under the curve. I can get the net. That makes sense, okay? But I can be discontinuous as long as it's a jump discontinuity and there's a specific number of them. I mean, there could be 100 of them. There could be 1 or 2 of them. What is a jump discontinuity? It looks like this. When you get to a certain value, it jumps up or down to some other value. What? Can't have 2.
So you can take the area of that?
I can take the area of that, even though there's a jump discontinuity. Because, look at this. I can do rectangles here. I can do rectangles here. Sorry, I'm trying to show. There's just a jump right there. But the area at any one point is basically not anything. So I can still get rectangles. What I can't do, if there's not a jump discontinuity, like if there's a asymptote, that's not a jump discontinuity. Or if I go here to here, and then I pick up over here, I can't do that. I can't do those. Because there is going to be a gap here. There is going to be a gap here. Well, maybe we could do this if we do it separately. But as long as it's just jumping up or down, I can still do it. But you got to have a finite number. I can't say it jumps up and down infinitely number of times. But anyway, continuous, even if it jumps up to another, I can still do my rectangle. I can still find the area under that curve that's in pieces, because there's no gaps in it. I couldn't really say find the area between A and B here, because there's a gap, or A and B here, because there is somewhat of a gap. They're never gonna meet up. Here, there's not really a gap in the X. So, jump discontinuity doesn't have any gaps in the X's. Does that make sense? My X's technically still go the full distance. It just jumps up to a different one. Okay, so anyway, yeah, so I can do it for that too. So I can do the integral for a lot of things, in other words. Just remember it's net area, so area above minus area below. To simplify the calculation of an approximation, you're gonna see on the test, I see a lot, I just put this on here. You're gonna do Riemann sums from right or left endpoints of rectangles. That's probably what you're gonna see most of. Yes, I had you practice trapezoids and Simpsons, and even midpoint. But remember how to do that? The integral, we're gonna estimate that, I should have put estimated by summing up between 1 and however many subintervals I have. Height, width, hopefully my width is gonna be the same each time. Okay, I should probably change that to approximate, sorry. Approximate. All we do in general, we replace the sum up with this symbol, the integral sign. And the width, the change of x becomes dx. So notice that became different. I keep my function. And that becomes that. This will give me a more exact, will give me the exact value. This is giving me a pretty close approximation. Cool. We can look at this example tomorrow. I just want to pull everything together.
Wait, what's that mean at the end? The S subscript I.
So that's the first value of x is what that means.
Oh, initial.
So yeah, you're gonna start with the initial x and the change of x. So to go to any value of x, take what you started with and add the change of x to it 1 time, 2 times, 3 times, and then you're at the next value of x. Yeah, but if you have your change of x, you're just gonna go that. Basically, that's what that's saying. That's saying, once you have your change of x, you're gonna go that much further, that much further, that much further, that much further, until you get to the last one. That's all that is. Okay. So, for approximating, we're changing our summation, sigma, to integrals, or a change of x to dx. But if they say, approximate this thing, hey, we have 5 methods now we can approximate. But if they say approximate, they're gonna probably gonna tell you how they want you to do it. Right, left, midpoint, trapezoid, Simpsons. Okay, this is the stuff I'm not gonna show you. I'm debating. Okay, I don't know if I'm gonna show you that. That looks more confusing than it's probably worth. Because I wanna show you something else. Okay, we'll work through these examples tomorrow. I did assign an AP video, if you wanna see somebody else doing Riemann sums, and this back and forth between summation versus integral. Here's a video I've assigned to look at. Okay, in addition to the rectangles, right, we have the midpoint, which is still a rectangle, trapezoid, and Simpson's rule. Okay, we practiced that. Here's what I want to show you. I think this is the last thing I want to show you. Yeah. Oh, I haven't assigned the other video yet, but I'll pop that in there too if you want to see both. There's 2 of them in this section that kind of sums up everything. So if you take 6-1, 6-2, 6-3, and put it all together in 6-4, you're all caught up. But I do want to show you this. This is good stuff here. And if we don't have time to write it all down, there's a lot of stuff here. This is all common sense as I go through it, but it's good stuff. This is the stuff that I kind of came from here. But, hey, we do want to know this. Remember, the integral goes from the lower bound to the upper bound. So what if they have the upper bound first? It's going backwards from B to A. Oh, it's easy. It's the opposite of what it was, A to B. Just stick a negative out there. That's all you gotta do. So it's like you're taking it away. So if you see, hey, the big number's on the bottom, it's not on the top, which we'll eventually see, I will remind you, oh, all I have to do is flip it and do the negative. It's the opposite, that's what that little symbol means now in higher level math. At first it meant minus, then it meant negative sign, then it meant the opposite of it. I'm just gonna do the opposite. I'm gonna go from the small number to the big number and just put a negative in front. The reason might be when you go from B to A, if you think about it, I might be getting a negative number here. So if I do the opposite of what I've gotten here, I've got a positive number. Again, this makes common sense if you think about it. If A and B are the same number, I'm going from x equals 3 all the way to x equals 3. What's the area underneath that? Well, I haven't gone anywhere, so there is no area. Yeah, so if these two are the same number, you haven't gone anywhere. So the area under the curve, nothing. Okay, what if A and B are not the same thing, but I'm taking the integral of a constant? The constant times the length of the interval. Well, that means the constant's always the same height. So all I have to do is height times width. That's just the area of a rectangle, because the whole thing happens to be a rectangle. I just got a flat top here. Okay, that's common sense.
Is this on campus?
Yeah, this is on campus. It's also in the textbook, all these rules, but they're pretty much common sense. Hey, if I want to take the integral from A to B, as long as they're not the same thing, of two different functions, added together, I can break them up. I can take the integral of this one from A to B and the integral of this one from A to B, and then add the two answers together. That'll be helpful. Hey, I could do that for derivatives, right? I could break up I could take the derivative of this one, the derivative of this one, and the derivative of this one, and add them together. I was doing it a lot. I can do the same thing for integrals. Take the integral of the pieces, and then add your answers together. It's oftentimes easier than looking at the whole thing. Ooh, look at this. If I have a constant times an integral, I can pull that constant out and just take the integral of the function and then multiply by what I pulled out. That's what we did for derivatives too. Don't worry about the constant, pull it out. In fact, we kind of did that a little bit when we were doing antiderivatives, right? Hey, we're going to put this here and then we're going to take the antiderivatives. Oh yeah, I pulled a 4 out. Okay, that kind of makes common sense. I bet this one makes common sense, because this is just the flip side of, hey, if I'm adding to, I can do the same thing if I'm subtracting to. The integral of one thing subtracted from another, I can take the integral of the first one, subtract the integral from the second one, or subtract the two answers. That's easy. That's like that other one. This one's cool. We often forget this one. And it's probably more used to us going the other way, reading it from right to left instead of left to right. The integral from A to C plus the integral from C to B should be the same integral from A to B, because you're picking up at the same spot. So you got this piece and this piece right next to it. Well, I should be able to just go from A to B. But if you read it from right to left, if I want to go from A to B, sometimes it's really easy to go from A to some point in the middle, and then from that point in the middle to the other piece. Especially when you have a jump discontinuity, I can figure out, I can probably go from here to here pretty easy. And I can probably go from here to here pretty easy. And then I'll just add this piece to that piece. And this would be my C. Sometimes it's easier to do that. Treat that one as one. Treat this one as a different one. Get the two integrals, add them together. So sometimes reading it right to left, I can break it up. Yeah, you can get the pieces and add them together. Yeah, as long as you're connecting them, where this one left off, this one picks up. But we're gonna see, it's probably gonna help us if I read it the other direction. Let's see, what else? Hopefully all of these are sort of common sense, like what you would need to do, especially having worked with some of your readers. Bless you. 3 more, okay. So, if a function is greater than 0 in the interval I'm interested in, then its integral will be greater than or equal to 0. I don't know. Planning on what's coming up, I don't know how many times knowing that is gonna save you. I don't know. It's true, yes, it's true. I don't know if it's gonna save you. But that leads into this, hey, if this function is bigger than this function, the value of this function is bigger than the value of this function, at least in the interval I'm interested in, then the integral of this function is gonna be bigger than the value of the integral of that function. Okay. Again, I'm not sure how often that's gonna save me in the future, but it is true. And then if a function is in between two values, then the integral is in between those two values times the width. Again, these last 3, I don't know where they're gonna save you. I know what's coming up. Do I have to know that it's gonna save me somewhere where I need this to figure out the problem, or I need this to figure out the problem, or I need this to figure out the problem? Probably not. Everything else, man, they're time savers. And you would probably even do it, not even had I listed them, you probably would have done it that way anyway. So they're common sense rules that you can use, very similar to derivative rules. But when we get in and we start playing around with this stuff, yeah, you're gonna forget that I actually broke this stuff down. And you'll probably not really see these too much, these last 3 anymore. So I did wanna hit you with those 3, and then we can play around with it tomorrow, with these examples, okay? But we are still approximating, guys. So, if you've not gotten the practice with rectangles, trapezoids, parabola, Simpson's rule, get the practice. It takes a while. Get the practice. Get the practice. I'm giving you 2 more days to get the practice than I had originally planned.
There's an extra one.
Yes. And so if you look at my assignment here, it's what I'm gonna have to do here. More stuff. Yeah. You got the practice.